In today's lesson, we're going to be looking at a small activity to help us distinguish between two different types of relationships. So again, we're still dealing a little bit with the idea of patterns and coming up with rules and looking at tables that are associated with those rules, looking at graphs. But now we're going to look at some terms that we can use to describe these relationships. We've talked a little bit about those before when we've looked at some of our scatter plots and our graphs. We've talked about the constants and the multipliers and how they can affect the relationship or the pattern. We're going to look at another set of terms here. So what we're looking at is we're looking at a single pattern, and we're going to be counting the position numbers and the squares of different parts. So in the first table, we're going to fill out the position number and the squares around the border, so in this case the gray ones. And then in our second table, we're going to be looking at the position number and the number of squares on the inside, so the yellow ones. We are going to be looking at how many squares are added between position numbers, or what the numbers change by. So we look at position 1, 2, 3, 4, at least for the ones that we have now. If I look at the gray squares, I see 1, 2, 3, 4, 5, 6, 7, 8. 8 in the first one, then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Third one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we're starting to see a pattern here. You might see a pattern here. I'm going to go ahead and assume that the next one is 20. Based on the pattern that I'm seeing. If you can't quite see the pattern, again, this is where the second column, or the third column can come into play. How many squares are being added between position numbers? So what are we increasing by? We're increasing by 4, increasing by 4, increasing by 4. So from our understanding of patterns and rules, we can assume, or we can see, that they're all going to be increasing by 4. So if I go through and continue the rest of my table, I get 24, 28, 32, 36, 40, and 44. If I'm looking at the squares on the inside for the next table, or the yellow squares, position 1, I have 1 square. Position 2, I have 4. Position 3, I have 9. Position 4, I have 16. So we might be able to see what the pattern is going on, or how things are changing. If not, again, let's take a look. How many squares are added between each one? Well, I'm adding 3. Then I'm adding 5, then I'm adding 7. We can see how they're increasing, so we might assume that the next one, I'm going to be adding 9, right? Because how much we add increases by 2. So I'm going to be adding 9 this time, then 11, then 13, 15, 17, and then finally 19. So in the end, we can use this increase to tell us how many squares are going to be in each position. Or you can go through and actually draw them out, or you might recognize what the rule is by looking at it visually. Right? So if we take a look at it, we would have 25, 36, 49, 64, 81, and 100. So we'll worry about what the rules are for each one later, but you may already be able to guess what that is. Now that we have our table for that, we want to be able to graph it. So let's graph our two different tables on each one. So the squares around the border, at position 1, we had 8. 2 was 12. 3 was 16, 20, 24. You see we're just going up by 4 every single time. If I want to work backwards, I could as well. So at position 0, I should have 4. And I see that I get a nice straight line. In my next table, or graph, sorry, I'm going to be graphing my second table. So 1 and 1. So say about here. 2 and 4. 1's probably a little bit lower. 2 and 4. 3 and 9. 4 and 16. 5 and 25. 6 and 36. 7 and 49. 8 and 64. 9 and 81. And then finally 10 and 100. So here, if I try to connect all my points in a line, this is the representation that we get for this one. So what relationship do you see? Linear, straight, or nonlinear? Right, so looking at the two, if we go back and we look at the graphs, hopefully we recognize that the one pattern forms a straight line, right? Even though we may not have drawn it completely straight, we should recognize that this is still a straight line, especially when we compare it to the second one here. This is not a straight line. Hopefully you can definitely see that curve in that line. So the squares around the border is what we would consider linear, and the squares inside are what we consider nonlinear. How can we describe the pattern or relationship for each? Well, for the squares around the border, you would say that, again, we've already described it as linear, but we could also say it increases by the same amount each time. And for the squares inside, or that second example or table, increases by a different amount each time. Is there an equation that you can use to describe the pattern? So again, if we go back to our first table, if we look at the pattern, or we look at the tables in particular, we already know that it's changing by 4 every single time. So because of that, we know, or we should recognize, that our multiplier is going to be 4. So we should have something along the lines of y equals 4x, right? 4 times the input number or 4 times the position number. If you prefer, I can put it as tiles equals 4 times the position number. And we should recognize that we still need a constant. If we go back and look at our graphs, we can see that our linear graph does not cross through 0, so there is a constant involved. And if we go back to our table, we could see that if I go back to position 0 and reverse everything, I should end up with a value of 4 when the position is 0 or the input is 0. So working back that way, I should recognize that I do have a constant. I could also try and multiply each position number by the multiplier and see if I get my value. Right? 1 times 4 does not equal 8, 2 times 4 doesn't equal 12, and so on. So there has to be a constant involved. And in this case, it's going to be 4. So my rule would be y equals 4x plus 4, or we could say t equals 4p plus 4. Again, same idea. We have, let's color code it, our constant, remember, in green, and our multiplier or slope or rate of change in red. And we can also say, we also use the term constant or y-intercept. We've talked about that term as well. And if you want to challenge yourself, you can try to figure out what is the rule or equation for the squares that are on the inside. So if we go back up and look at our table, it might be a little difficult because we don't have a common multiplier here because it's adding or increasing by a different amount every single time. So we don't, or this doesn't follow our standard rule. But what you might be able to tell is if we look at the visual aspect of it, the inside squares form a square themselves, and it's all dependent, or the size of it is dependent on the position number. We have a 1 by 1 square in the middle, a 2 by 2, 3 by 3, and 4 by 4. So we do have, or we should see that kind of pattern of we have a square in the middle, and the size of the square is based on the position number. So if I go down back to my rule, I might say my rule is something like y equals, and how do I show that the position number becomes a square or multiplies by itself? Well, I could say x times x, or if I want to shorten that, I might say x squared, because x squared just means x times x. Or if you prefer, we can say the number of tiles is equal to the position number squared, because p squared is just equal to p times p. So that is the pattern for the squares on the inside. So the main idea here is to look at two different tables, two different visuals, two different graphs, two different rules, and identify what makes a linear relationship and what makes a non-linear relationship. Because based on what we see or what we found for our squares around the border and our squares inside the border, we've found, or we've come up with, or we should have come up with, some key identifiers of, again, linear and non-linear patterns or relationships. We won't worry too much about the extension questions. We'll just jump right into our summary. So if we're looking at a linear versus non-linear summary, right, so we're going to look at all the different representations. We've talked about them, and we've looked at them in the past for linear relationships. Now we're going to look at them all for, and comparing between linear and non-linear. So for a linear relationship, if we have a graph, we should see a straight line. If it's non-linear or not a straight line, that's what we should see in the graph. So visually in the graph, it should be very easy to tell if it's linear or non-linear. Depending on what we look at, if it's like looking at a scatter plot where we're looking at data, your line may not be a perfect straight line, but it should generally form this kind of trend, right? It should be kind of obvious that it's a straight or fairly straight line. If it's non-linear, it will be clearly non-linear, something that will kind of show a curve in it for sure. When we're looking at an equation, right, a linear equation, the variable or the letter has an exponent of 1. So that means our pattern or our rule or our equation is going to follow what we've been looking at so far, which is the y equals our multiplier times x plus a constant. Our linear pattern is going to follow this rule. Now, we may have a multiplier of 0 or a constant of 0, but as long as it follows this general pattern, it is considered a linear pattern or relationship. And the other thing is, when we're looking at a nonlinear one, there's at least one variable that has an exponent greater than 1. So if we look here, even though the second part, 2x plus 5, is similar to what we've seen in a linear pattern, this 3x squared here is also included. So this part right here is what makes this equation or rule nonlinear. Now, you don't have to worry too much about being able to determine a nonlinear rule for a specific pattern. We're not going to be doing that in this course, but the main thing is that you recognize what a nonlinear equation or rule is when compared to a linear one. So if I were to give you two equations, could you tell me which one's linear or nonlinear, or both of whichever type? Right, so can you distinguish between the two if you're given the equations or the rules, or if you're given the tables or the graphs? When we're dealing with a table of values, we're looking at what we call the first differences. So the first differences are basically what are we increasing by every single position increase. So here we're decreasing by 4 every single time. This change is what tells us if it's linear or not. Because they're all the same, it's considered linear. So the first differences are what we were doing here. Actually, let me use a different color. So if I do the same thing for a nonlinear graph, the first differences are not the same. And when we look at the pattern, we see -3 to -1. So that's an increase of 2. From -1 to 3, that's an increase of 4. From 3 to 9, that's an increase of 6. And from 9 to 17, that's an increase of 8. Now the key thing here, even though that this shows the correct examples, we want to be careful of what the x values are, or the input values, because they need to be increasing by a consistent amount in order for this kind of identifier to work. So our x values, or input numbers, must increase by a consistent amount. So if we look at the first table, they're increasing by 1. If we look at the second table, they're increasing by 2. Or sorry, I should say increase or decrease, depending on what our table is showing. But as long as they're increasing or decreasing by a consistent amount, and the first differences are the same, then it's linear. If they increase by a consistent amount and the first differences are not the same, it's nonlinear. And then finally, when looking at a visual pattern, again, this one hopefully will be easy to tell. And if it's not, you can always revert back to the other representations, because at least you should be able to convert any pattern to a table between position number and number of figures or number of tiles, and convert that to a graph. You may have trouble getting it to a rule, but if you can get it to a table or to a graph, hopefully that will help you determine if it's linear or nonlinear. But if you're just given a pattern and you're not allowed to do anything else, remember, a linear pattern grows by the same amount for each position number, and a nonlinear pattern does not grow by the same amount for each position number. Because we can see here, we increase by 1 shape, increase by 1. I'm counting 1 triangle and square as a single figure or single tile. And when we look at the nonlinear one, we've increased by 3, and then we've increased by 5. So we're increasing by different amounts. So again, looking at all those different representations, the visual pattern, the equation, the table, the graph, you should be able to identify if a relationship or a pattern is considered linear or not. Again, we're kind of building off of those multiple representations that we've talked about before, and just adding some new terminology on how to describe those relationships that those representations represent.